In modern households, batteries have become a foundational component of everyday energy use. From small portable devices such as remote controls, flashlights, and wireless accessories to larger applications like power tools, laptops, and residential energy storage systems, batteries operate quietly in the background of daily routines. Their presence is often taken for granted, yet they support a wide range of functions that define contemporary living. The increasing adoption of renewable energy technologies has further expanded the role of batteries inside homes. Solar panel systems, for example, are frequently paired with storage solutions that allow excess energy to be saved for later use. This shift reflects a broader movement toward decentralized energy production, where individual households play a more active role in managing their own power resources. At the same time, consumer electronics continue to evolve toward cordless and portable designs. This trend increases reliance on rechargeable batteries and places greater importance on how these power sources are used, maintained, and eventually replaced. Despite their growing importance, many households interact with batteries in a limited and reactive way. Most attention occurs only when a device stops working or when a system no longer holds a charge. As a result, battery usage patterns tend to form around convenience rather than long-term planning. Understanding these patterns provides insight into how energy is handled at the household level and how everyday choices influence material consumption, waste generation, and system reliability. The most common approach to household batteries is straightforward replacement. When a battery no longer performs adequately, it is removed and exchanged for a new one. This applies across a wide range of products, including disposable alkaline batteries, rechargeable lithium-ion packs, and sealed lead-acid units used in backup systems. Charging practices represent another widespread pattern. Many people charge devices whenever a low battery indicator appears or leave them connected to chargers overnight. These habits are usually shaped by convenience rather than technical considerations about optimal charging cycles. For households with larger energy storage systems, basic monitoring through built-in displays or mobile interfaces is common. Users often check overall charge levels and rely on automated system controls to manage daily operation. Storage behavior also plays a role. Spare batteries are frequently kept in drawers, toolboxes, garages, or utility rooms, often mixed together regardless of type or condition. Over time, this results in collections of batteries with varying states of charge and unknown performance. Across these approaches, simplicity and immediacy tend to guide decisions more than structured evaluation. While these methods are practical, they also present limitations. Routine replacement increases demand for raw materials and contributes to waste, particularly when batteries are discarded without assessment of remaining capacity. Charging habits that are not adapted to specific battery chemistries can gradually reduce performance. Repeated exposure to unfavorable charging patterns may shorten lifespan, reinforcing the perception that batteries are inherently short-lived components. In larger storage systems, limited engagement with diagnostic tools can make gradual degradation difficult to detect. Small declines in capacity may go unnoticed until performance drops below a usable threshold. Storage conditions further influence longevity. Heat, cold, and long periods of inactivity can negatively affect battery health. Yet these factors are rarely considered in everyday handling. Together, these structural limitations illustrate a gap between how batteries function and how they are typically managed within household environments. Within sustainable energy and resource management discussions, batteries are increasingly viewed as assets that can be evaluated and maintained, rather than immediately replaced. Some approaches emphasize testing and inspection to determine whether a battery still holds usable capacity. Others focus on learning how different battery types respond to charging, storage, and usage patterns. There is also interest in extending the usable life of batteries as part of broader circular resource strategies. In this context, batteries are considered part of a material flow that benefits from careful handling and informed decision-making. These perspectives do not replace conventional practices, but exist alongside them as alternative ways of thinking about household energy components. In discussions about battery maintenance and reuse, some people reference a resource called New Battery Reconditioning Course as material that addresses general methods and concepts related to evaluating and working with different types of batteries. It is typically mentioned as an informational resource that outlines technical background and procedural frameworks associated with battery reconditioning topics. Household approaches to battery use and maintenance vary based on technology, living conditions, and individual preferences. Some households rely primarily on replacement, while others explore evaluation and maintenance practices. These differing patterns reflect a range of constraints and priorities rather than a single standard method. This video has presented an overview of how battery usage patterns are commonly discussed within modern homes for informational purposes only.